All right, we're going to go ahead and open up two terminals. So this is how we're going to get started. So however you log into Hyak, I want you to do that now. I'm going to have two terminals open. One of them we're going to use to monitor the queue for Slurm, and the other one we're going to use to edit and move around, navigate the system. So I'll try to make these as big as possible. This one in front I'll use as my main terminal, the other one I'll set up. So just have these ready, and we're going to log in with SSH, your username at clone.hyak.uw.edu, and then you'll need to put in your password, which will not show, but it will have a little key symbol, and you'll do Duo two-factor authentication. So I got one there. I'm going to do the other one. So I'm just going to keep that one in the background. Have you all used Hyak before? You're all Hyak users? Okay, good. So this is an advanced tutorial, as I said, so I won't be spending too much time on the basic stuff, but we are going to be talking about Slurm, which is Hyak's job scheduler. It's a tool that helps us to take in user requests, all of the specifications that they want for their job, how many nodes they need, how many CPUs or GPUs they need, how long they need that, and then in that system is where you'll execute the command that you're trying to do for that job. And so the first stop for anything with Slurm is always to use Hyak alloc, which will look different for everyone. I am in the UWIT group, and also I used to be a postdoc in biology, so I'm in the Wasser lab as well. They haven't kicked me out yet. So these are the accounts that I'm a part of and the partitions that I have access to. If you are a demo account user, yours will just say demo and pending, and then we'll talk. Do we have any demo account users here today? No? Everyone has a fully accessible Hyak account? Okay, so we won't spend too much time on the demo account stuff. But demo account users, the intention of that is for them to be able to try out Hyak systems and see if it's working for their protocols. And so they have more limited access, but they can always use the checkpoint queue. For today, though, since you're all users, you will want to pick one of these different partitions to submit jobs to, because you will have faster and priority access to those queues. Checkpoint, I would really say save that for maybe many jobs after you have your workflows kind of going that you don't need results right away. But for this tutorial, we'll want to have quick access so we can get our job done. All right, and so the first thing that I want to do is have everyone set up their working directory and get to the materials for this tutorial. And so if you all have a space to store your data for this tutorial, that would be great. So I would recommend not using your home directory, which is represented by the little tilde symbol. It's the place where when you log in, that's where every user has this home directory. You have a limit of 10 gigs of storage there, and if that fills up, you're really limited to everything that you want to do on Hyak. And so if you're all parts of different accounts, then you probably have a gscratch directory where you can store your things, or if you want to use the free storage that we have, that's in gscratch scrubbed. And so I'm going to make a directory in gscratch scrubbed today, and I'll be demonstrating that, but if you have a different place that you can store your files, please do that. So I'm going to change directory with cd to gscratch/scrubbed. And in here, I already have a directory for my username, but if you don't have one, you can make dir, make a directory, and you can put your username here. I'm not going to do that. I already have one. So I'm just going to change directory and go into Finch KN. And then we'll need to copy the materials. So you go CP for copy, recursive with a -r, and the full path for these materials are in /sw for software, Hyak 101, and then basics. So that is where I've stored all the materials for this tutorial for you, and you're just going to say here with a dot. That will say, I want to copy all of the materials from there to the directory that I'm in. All right, so now if I ls, I see that that basics directory is there. I'm going to change directory into basics, And now this is going to be my working directory for today. I'm going to conduct all of my work in gscratch scrubbed Finch KN basics. Yours all will look different for you. All right, so let's see what's in here. I'm going to use lsltr to give me the long version of what the files are in here, and it's going to sort them with the most recently edited things at the bottom and the later edits at the top. So for today, we're going to be using a container called Locator, which is here. Your container files are always ending with .sif for Singularity image format. And so Singularity is the old name of Apptainer, which is our container runtime software. Are you all familiar with software containers? Okay, so it's an isolated software environment that has the software that you're wanting to use and all the dependencies. And you can also have a distinct operating system than the operating system that Hyak runs, which is Rocky Linux 8. All right, so this container it's containing basically it's Python TensorFlow, but it also has some scripts from out of workers at the University of Oregon that have developed this neural network that takes DNA sequences and also the locations on the map of where those DNA sequences were collected from organisms from any population, and then it builds a neural network to try and predict where each one of the DNA sequences could have originated. And so the example that I have for you today is with black cottonwood trees. So this is a Pacific Northwest native tree called Populus trichocarpa. And so the data set that we're going to be looking at today has DNA from 425 trees, so individual trees. And we have the locations for where all of those trees are planted. Or not that they were planted, but they were, they're wild trees. And so we have DNA from them, we have their locations, and we'll be testing in different subsets how well the neural network can predict where that tree was located. So that's just our example for today. As a postdoc in biology, I was doing something similar, but for elephant tusks. So trying to predict where the ivory, which population of elephants could have produced that ivory to try and combat wildlife crime. All right, so full circle, I'm a researcher just like all of you, and this is this example is based on work that I've done, so I hope that this is helpful for you. But the main idea for today, the main objective is for you to have these template scripts so that you can have an example for how to use our job scheduler in a more advanced and really kind of step up, level up your skills and make the most of your time, and also leverage that you can do a lot of parallel computing with our HPC supercomputer Hyak, right? Any questions before I move on? So what I'm going to do next is we're going to walk through all the types of Slurm jobs that are available. So an interactive job, a batch job, which runs in the background, and an array job. And then in the final module, we're going to be using some more bash scripting to really make the most and leverage scripting with our job scheduler. Okay. So first of all, we want to start I'll be walking through all of the different things that we have here in our tutorial directory. But we're going to start by starting up an interactive job. And the command to do that with Slurm is salloc. So I'll be using my own account, and I encourage you to use your account, but mine is, if I go --account equals uwit, yours might be stf or some other directory from your lab, --partition. As I said when we were looking at Hyak alloc before, you have the list of partitions. I'm going to be using compute, so equals compute. And I'm just going to ask for one CPU on this task, so CPUs per task. It's plural, CPUs per task equals 1 --mem for the RAM. So this isn't your storage, this is your working memory for processing your job. So RAM, 5 gigs. And it always needs the units there. The default units are megabytes. So if you don't put a capital G next to it, you'll just have 5 megabytes, which will make things a lot slower, right? And then --time. We're just going to keep this open for 20 minutes just for now. So an interactive job with Slurm is something that you want to use if you need to do a lot of debugging with your code in real time. So the rules on Hyak is that you always log into the login node, right? But you want to keep that for everyone. It's the front door of the cluster, so we want to keep traffic pretty clear. There are some operations that you can do, but any heavy computing, you want to open up a compute node, and that's what this type of command is going to do for you. And so you'll see that things are going to change a little bit, but the use of this is if you're really just troubleshooting, trying to get your commands right, this is where you want to be doing all that work. And then you'll be using scripting later to submit these jobs that are longer running and take more time. All right, so I've executed that. It tells me that it's granted, and it always has this job ID. This is really good information for us. If you have something that is not behaving the way that you think that it should be, something weird about your jobs are not getting filled or lasting as long as you expect. If you have this job ID, that's really good information for us at the help desk to be able to look into the logs that we have access to and get you an answer about what's going on. But now you see that my address, or who I am on the cluster, has changed. I'm still Finch KN, but I'm no longer at clone log n3. I'm at n3043, and I'm still in my basics working directory. So I've changed my position in the cluster to be in a compute node now. All right, so again, we have our tutorial docs here. The first thing that we need to do to use Locator neural network. Oh yeah, you have a question?
So I have logged in from my labs account. We both are on the same node.
Yeah.
Was that possible?
Yeah, so the way that Hyak works is that your labs are all buying like different portions and adding that hardware in. But really it goes into a pool of resources that are available to you. So it's a pool of all the like resources. So if you requested a compute node, there's like hundreds of them. And so it was just that the first available that we both were able to get on was N3043. If your lab, for whatever reason, had some federal agency saying, hey, we helped you buy that hardware, like tell us what the host name is, we can do that for you. But you should know that your jobs will probably get filled by any number of host names. Okay? Yeah. All right, so the first thing that we need to do for Locator neural network to work is that we need to make an output directory where all the results will be stored. So we're going to make dir out. It's just going to be called out. And now if I ls again, I see that I have this directory called out. All right. And with Apptainer, with containers, there are also ways to use them interactively. So you can send your commands from outside to be executed within the container, but you can also interact with the container as well. You can get inside and you can do stuff in there. And so that's what we're going to do. We're going to use Apptainer, our container runtime software. We're going to open up a shell. A shell is basically just your view into a cluster like this, into a server. So this is a shell terminal, right? And then we're going to go clean env. This is important for the Locator container. There are some environment variables within the container that are in conflict with outside. So if you do clean env, none of your environment as a user on Hyak will be carried over. We're going to bind the gscratch directory. Binding the directory is very important. It's pretty much a prerequisite for using containers anytime you want to, all the time. The container is isolated. It doesn't have any of your files on the outside accessible to it within the container. So by binding our file system, just by giving it bind gscratch, you're able to make all of the files that we have listed here accessible to the container, which is important, or else it won't be able to do what we ask it to do. And then we're going to provide our container file locator.sif. So this is the command apptainer shell clean env bind gscratch, and then locator.sif. And now you see that my command prompt has changed again. Now it says apptainer. This is how I know that I'm actually in a shell in the container now. I'm not in Hyak anymore. I'm going to go ahead and clear my screen just to make more space. And we can go ahead and start listing some of the files that are within the container. So if I ls/ or ls the root directory of the container, I see there's a lot of things that I would see in Hyak itself, right? Like I have mmfs, that's our file system. I have bin, I have all these things that are standard in Linux environments. But I also have this locator directory, and that was actually what came with the software to be able to run things. So now if we ls/locator, we can see inside, this is all the information from the GitHub repository that I used to install this, this software. And I see they have a scripts directory within there. So if you see, I just did up arrow, so I can go back in my history and get a command that I already did. So locator/scripts, this is where I have the locator.py Python script that we're going to be using for the rest of our commands. So the point of this is just to give you a little bit of background on containers, that this doesn't exist on the file system except as that locator.sif file. But I can shell inside, I can see these isolated files to run this Python program that we're going to be using for the rest of our demonstrations. Okay. Another thing that you should think is that, oh, well, there must be Python in this directory as well, or in this container as well, and there is. If we execute Python, we see we actually have an older version of Python, Python 3.8, and we have the Python shell here. So if you wanted to execute Python commands with the libraries that are installed in this container, then you would be able to do that. So to exit the Python shell, you can do Control plus the letter D, or you can type exit. All right. So that's a little bit about the container itself. Let's talk a little bit about the files that we're going to be using. So if I ls again, remember I'm still in the container, but I have access to all the files that are outside of the container in my working directory. And we have this directory here called data. So let's ls data. And POTR is actually the abbreviation that I've used for Populus trichocarpa, which is black cottonwood trees, the Latin name of those. So we have the data set here is poder _ genotypes 1000. So I've subset just 1,000 SNPs or mutations from these trees so that our exercises move a little bit faster. I do have the full data set here. I wouldn't say use it today, but later on if you want to try out testing out a neural network and really throwing everything at it, this data set has information from over 30,000 genes. All right, but let's go ahead and do ls-l data and then poder genotypes 1000. So this is just a word count, all the lines in the genotypes file, to show us that we have 425 trees that we've gotten this DNA from. And I'm using up arrow again, and I'm just going to edit this command to look at the top of this genotypes file, just the first 3 lines. So you can see it's got all these scaffolds, so these are actually gene models, gene names, and then the name of the tree is here, and then all of the genes are coded in dosage format, which I won't go into because it's out of the scope, but just know that these numbers are signifying if it's a ATGC and if it matches the reference genome or it doesn't. Okay. And now let's ls data again. So we also have these pred files, and we'll look at the top of one of those. Head data poder m pred 1. So this is what every single file is, all of these 0 through 4 pred files are going to look like. It's the information, the latitude and longitude coordinates in decimal degrees for all of the trees where they came from. So the x coordinate, right, is longitude, and the y coordinate is latitude. And if you know where you are in the world, we're not too far away. So northwest hemisphere is kind of where these trees grow. Actually, this data set was collected in British Columbia. Okay. And you'll also notice that some of the trees have NA. What we're doing here is we're marking these are known location trees. But for each one of these pred data sets, we have asked a different subset of 10% of the trees to be marked as unknowns as a blind test. So we're going to take all of the DNAs and all of the known locations and build a neural network, and then we're going to ask Locator to predict the locations for these unknown ones. And we're going to do that with multiple random draws of these 10% of individuals, so we get a distribution of the error for where these trees have been, or where it's predicting these trees could have been. All right, and the reason we're doing that is, right, if you know about neural networks, there's some randomness where it starts, there's some randomness in what tree it starts building the network with, and we really want to get a full distribution of the error. And the error is measured by when it gives us our predicted latitude and longitude, and we do know where CHW275 is. We can measure the distance between known and unknown as the crow flies and get that measure of error. And how good was the Locator neural network at predicting the location based on the known information that we gave it. All right, so that is the full background of what we're doing. But like I said, the reason that we're doing all of this is to learn about Slurm. But first, before we do that, I want to run this. So just to demonstrate that we have this interactive job going on Slurm. We're inside of the container, so we can run commands within the container and see what happens. I'm going to go ahead and show you what our main command that we're going to be going back and forth to with Slurm is going to look like, and we're going to execute that in our interactive job. All right, so the command looks like this. We're going to call Python. And we're gonna, inside of the container, right, I showed you that at the root, there's the locator container, or locator directory, and then a directory with scripts. And in there, there's Python script for locator.py. That's what we're gonna run. So we're gonna go locator here. We're inside of the container, scripts, locator.py. And I told myself not to be so fast, but I do want you to know that you are able to use tab to tab complete and predict what you're writing. So that's why I can just start writing scripts and do tab, and it is filling in, you know, it's predicting what I want to do, like this. And next we're going to give it our matrix, which is our DNA file. And that is in data, like I said before, like we looked at, POTR, genotypes, and remember to put the 1000 because it will take a little bit longer with the full data set. And for our sample data, so these dash here, these are all coded into the Python script itself. So these are like the arguments for the Python script. These are not, you know, my creations here. And they don't have anything to do with Slurm. So this one is going to be data / POTR m pred, we'll do the 0.text. Yep. All right, and lastly, we want to give it our output directory. So we're doing --out, out, /, and we're going to give it a prefix. So we'll tell it POTR predictions 0. And I just want it to match that our input sample data is going to be from the data set 0. So I want our output to also be marked as being from data set 0. Go ahead and execute this. It will start up in 10 seconds or so. It gives us a few, these are just standard TensorFlow warnings that say, hey, you don't have your GPUs on. Well, because we didn't request any GPUs for this job. If we had requested GPUs with the salloc, which would be to say --GPUs equals 1, and you'd have to pick a different partition, a GPU partition. For example, there's GPU -L40S, GPU A100, so you'd have to do that if you wanted to find the GPUs. So very standard again, TensorFlow, it's running through the epochs, it's doing the predictions here, and it ran pretty fast. We only gave it 1,000 columns in our DNA file, and the error is not so great. But of course, we only gave it part of the whole story for it to do this just as a demonstration. But after that, you would be able to use the results from this and make some kind of inference about if you thought this is doing a good job of predicting those 10%, or if you need to make some tweaks to the other parameters. But let's go ahead and look at the output directory, so ls out. And now we have these 4 files. So really, I'm just going to be talking about the pred locs, which is the predicted locations. These are our parameters for the JSON, or for the neural network, our history, and then there's a plot also. I won't be going over those today, but more information is available from the developers about those. So now, if we head just to look at the top of out/poder predictions, 0._predlocs, like this. Then we see we have our variables that we're wanting. We have longitude, latitude, and the sample ID, so that we can compare this set of predictions with the true location of where that DNA was collected and see how different that is and how well we did. So doing any post-data analysis is outside of the scope of this. We're going to continue using this same setup to talk more about Slurm. The next topic with Slurm is a batch job. So submitting a job to be executed in the background and unsupervised. This is ideal when you have jobs that have a very long runtime, that you don't want to be in this interactive node on the compute node for 10 hours or something like that. If your internet just wavers for a second, or your server alive, like connection with the server, goes out, that's just going to end before your work is done. So using a script to submit a batch job is ideal for what you want to do. So to exit the container, we're going to just use exit. And now we're back. We're still on our compute node. Before this next section, I want to set up our other terminal. And what I want to do in our other terminal is get the SQ, which is the queue, or how the job scheduler has scheduled your jobs. And we're going to put a watch command on that, which means that it's going to execute this command every 2 seconds, so that we'll be able to see when we submit our next job, it's going to pop up and be there, and we can look at it. Before we do anything on the other side, let's go ahead and set up our watch command. So watch, and then it's SQ -u, and then it has to be your net ID. So don't put mine, or else you'll see my jobs. Put your net ID there. So what you see here is the current job that I'm running on this side. I have the job ID, which we saw before. I have that I use the compute partition. It's an interactive job. The automatic default name for an interactive job is interactive. User, the status is running. It's almost done. We put 20 minutes, so this will finish on its own if I don't end it first. 1 node, and that's the host name that it's running on. So keep this up. We'll leave it on that side. We'll come back over here. We can go ahead and exit this job that is running. So now it says that it's relinquishing my job allocation from that job ID. I see over here now it's changed to canceling job, CG equals canceling. And I'm back on the login node. You can submit your batch jobs from the login node and everything else that we are going to do. All right, so in our tutorial directory, we have these scripts that I've prepared. So all of the scripts starting with locator NN are the ones that we're going to be going through. So the first one is locator NN_job.slurm. Just go ahead and copy that. And let's use Nano, which is a text editor, to open that. You can use Vim if you want to. I'm a Nano person because I like the simplicity of it, and it's nicer for beginners who I work with a lot. But you can choose whatever you want. Another reason I like Nano or Vim is that it gives me the color coding on my script, so it can help me to interpret what's going on here. So, submitting jobs to Slurm to run unsupervised, use the command sbatch. So all of these lines here at the top, these are called SBatch directives. These are the requests that I'm making about the job that I'm requesting that are coded here. So just like with salloc, where we saw this kind of notation, we're seeing the same here. The salloc commands and all of those flags, they're all the same as with SBatch. But we're going to set it up so that we can do something a little bit different. So one of the flags that I didn't demonstrate before was job name. So this is going to be called locator job. And then partition, I actually want you all to change this. So if you have an account and you're not just a demo, or you don't just have demonstration access, then I want you to put your account in this next section. So make a new line, start the new line with capitalized SBatch with the hashtag, pound symbol, and then put account, -- equals, and put your account here. The account I'm going to use is UWIT. It'll be different for you. You can use checkpoint, and we're going to be requesting so small amount of resources that I hope it will go fast. But if you do have priority on another queue, I encourage you to use something else. So I'm going to change mine to compute. I'm going to keep all of these the same, so we're going to do the same type of job as we did before. We're going to have one node. We're only going to have one task, or the same thing that we used before, CPUs per task is similar to this. And then 5 gigs of RAM. This is going to run pretty fast, as you saw, so I'm just going to ask for 10 minutes. And then this -out is going to take all of the standard output, so all of those epochs that were running when we ran the command before. This file is going to be made to capture all of that, so if there are any errors in there, I can look at it later. It's going to start a new directory called log, so we don't have to do that. This is shorthand for taking this job name. It's going to paste it here, underscore, and then it's going to take the job ID, which is going to be assigned to the job, and paste it there, .out. You can also have a -e variable, which will separate the errors and the output from each other. So you can have standard error in one file and standard output in another file, which can be helpful. Today we're just going to look at everything together. So any errors that we see and all the output messages are going to be together. So same thing as before. Instead of using apptainer shell, we're going to use apptainer exec, which is just to execute. So instead of opening up a shell, we're just going to give our command, tell apptainer to execute it. We bind our gscratch dataset, same as always. We're giving it again our locator.sif file. So kind of this part of the command was what we saw to get into the container before, but it's changed a little bit. And then this next part of the command is the part that we ran interactively before, where we're starting up Python, we're giving it our genotype matrix, we're giving it our sample data, and we're giving it output. This time we're going to execute on the number 2 data set. So it's going to be a different set of 10% of individuals treated as unknowns. For your use of this script later, I have explained all of the things in very, very much detail. So sorry about that. I would not cat that to your screen. I would just use Nano from now on. But just to make this generalizable and usable for everyone, I've put comments about all of this later for you to review later. All right, so if you've made all your changes and you're ready to go, we can save this. So I'm going to use the Control X to exit. And then it's asking me if I want to save this. I'm going to use Y to say yes, and I'm not going to change the file name. So now when we do ls-ltr, I see that that was the most recent thing that I edited. And it's ready to go, so we're going to go ahead and submit this job for execution unsupervised in the background. SBatch, I'm just going to go ahead and copy it, paste. And now it says that it submitted my job, and I see that it has appeared here, and it's pending, but that I have priority. So we'll see how long it takes. Any questions while we wait for that to get going? You all have submitted a batch job so far in your time using Hyak? Okay. Now it's running. Did you know about this cool way to monitor the queue? Okay, this is like my favorite thing ever, really. And it's cool when we start doing array jobs that you can kind of see them all come into view at the same time. Should be almost done. Let's see what's happening over here. So if we ls, oh, I'm going to do it nicely again, ls-ltr. Now I have my log file, right? So we'll look at that. Let's just go ahead and cd into log and ls. So I only have one output file there. You see how it did take my job name and it took my job ID? .out. So we'll copy this, and I'm going to use the more command because it's quite long, and then I can like kind of page through. So those were all the TensorFlow warnings at the beginning. We have 1,000 columns or 1,000 SNPs in our genotype file, 124 individuals. I think one individual got filtered out, and then it's diploid. It says it does some filtering, so only 989 of these 1,000 made it past their criteria. Now we see all of the epochs going, just like we saw before. If you use space, it like pages faster. Almost there. Okay, so then we see the same thing as before. Nothing new here. Let's cd, if you .. / you go one directory ahead of where you were, or before, closer to the root. ls out. And now we see that we have the same types of files. These ones for 0 were from our interactive job, and the ones for 2 were for the job that we just did. They all look the same as before. There's a lot of text wrangling to do afterward to do the data analysis to complete the full use of Locator. Any questions about interactive jobs? That was the basic stuff. That's basic Slurm, except that it uses a container. So you all have, passed basic Slurm now. Any questions? Good? Okay, moving on. Have you all used an array job yet? No? No? Yes, a little bit? No, not use array job. Okay, so I want to say what an array job is before we kind of get into it. Come on in. So an array job is when you use a single script to submit an array of jobs or a group of jobs to all be executed in parallel. So why to use this? Why to use an array job for Locator? Well, if we ls our data directory, let me do it in a better way. All right, so we have our 5 data sets here, which each have our different 10% of unknowns, or 10 test sets, you could say. But really, I'm going to do the same thing for each one of them. So I'm going to build the neural network with the 1,000 genotypes, and then I'm going to predict each one of these. So I could do a for loop, right? We all love for loops. You do one, it's done. Do the next, it's done. Do the next, it's done. But then that's going to take, what, like 5 minutes? They're not taking that long. But now, instead, I'm going to show you how to submit all of these at the same time so that you have 5 jobs running in parallel. This is called an embarrassingly parallel workload, in that it's kind of like you have your invitations to an event, and you have a bunch of them. And you need to put them in envelopes, put the addresses, put a stamp, so you get 5 friends to come over. And you can all work independently. You don't have to talk to each other. If you have a situation like that in your research, this is perfect for you. There's also other ways to use arrays. You can use the array variables to do math. So if you want to walk through different variables that are numeric, you can use it this way as well. I would encourage you to look at the basic Slurm tutorial where I actually use that type of example to set up the array. Okay? So come back to that later if that sounds like something that you need. But for today, what we're going to do is we're just going to be iterating over each one of these pred files with our job array. All right. So the array script that I've set up is here, Locator NN array. So let's go ahead and use nano to get in there. And we're going to do the same thing to set this up as we did before. So I want you to go ahead and add another line for -- account. And use your own account. Don't use UWIT. And compute is fine, whatever you have available to you. All of this is the same, but here we have our new variable array. This is what is setting up our array, and it's 0 indexed. So we actually have 5 jobs. These are going to be an index variable 0 through 5 that will help us to organize these jobs. And I'll talk more about that. A little bit different also with our log files. Same thing is true that the job name, which is now Locator array, is going to be pasted here. And then the capital A is still our job ID, just like we had %J. This one is our job ID, and then the little a is going to be, one of these numbers. So then you have all of your job file, or your output, all of your log files separated so that you can debug each one of them if you need to. We'll see that this is going to run pretty smooth. All right, so the first thing that we're setting up here is a file list variable. Are any of you familiar with Bash language, Bash scripting language? So we're going to be using that that language, that syntax today. And it's really perfect for working with Slurm. You can use Python and you can make scripts and stuff like that. But for this type of work, Bash scripting is really going to be your friend. So we're going to use that today. What this does is it's just going to list in one column all of the files that we talked about, all of those pred files in the data directory. So you don't have to stop your queue over here, but I'm just going to stop it so I can just show you what this does. All right. So if I copy this and I execute it, so basically this list is going to become a variable called file list. And Bash requires that you have this kind of notation. So you need the money sign to execute what's inside of the parentheses, and you need extra parentheses. Don't ask me why, I didn't write it. But anyway, this is what you need to make this work. So you're basically taking this list and you're putting into this variable called file list. Let me get my other command back. All right. Next, we're going to be trying to get just one of those files in the list and save it with our Slurm array task ID, which is the same as that indexing array 0 through 4. So we're going to be just attaching a number to each one of those lines in the file. So it's going to know that, oh, for number 0 in file list, that's going to be one of the files in the first job. And then the number 1 in the file list is going to be the file for the next job. This will become clear. I've got a table to show you all of this. I guess I have a table, but don't take my word for it. Tell me, is it clear so far? Okay. And then we're just going to echo this file into the log so that we know that the behavior is correct. And then it's the same command as we saw before, apptainer exec. We've got our clean env, our bind, our container. We're starting Python. We're giving the Python script. Same matrix file, but what we're changing here is instead of just putting in hard coding that input sample data file, we're passing it the file variable into that spot. And then we're still writing to the output. We're going to give it a different prefix. Instead, we're going to call these array poder predictions. And then to keep them all separate from each other, we're going to take that index variable again and attach it to the results. All right, let me pull up my table like I said I would. One more page. Here we go. All right. So for each job, the variables that we just set up, this table is showing what their values are. So for job 0 in the array, Slurm array task ID is going to be 0. The file is going to be the 0 indexed file in that list of file list. So it's the 0, 1. And then the output is going to be array poder predictions 0. That's going to be the prefix for the output and the directory there. For the first one, the next job in the array, Slurm array task ID is 1. it's going to grab this file as the input for sample data, and that's going to be the output file name. So those, we're only really making one variable. We're only making one change to the job that we did previously. And it's going to be to iterate over each one of these files. Instead of a for loop, which would have to wait for each one of them to finish, they're all going to be launched at the same time. Let me show you. So I'm going to Control X to leave, Y, keep it the same, S batch, Locator, NN array. Hold on, let me get rid of this. So I see this queue. So now we have all of them are under the same job ID, but now we have 0 through 4, that's our array. So they're all waiting pending, and you'll see once they're unpending, once they're ready to go, there they are. They're all running at the same time. So right, I think the first one that we ran took maybe 30 seconds-ish, 30 seconds to 40 seconds. If you waited for all of them to run serially, right, we would have 40 seconds times 5. We would have almost 5 minutes to run all of them. But instead, you're saving your time. You're leveraging that you have access to this supercomputer, and you're executing all your things at the same time. Okay. Anyone think that this is going to be directly applicable to their stuff? Do you have a kind of workload like this? Okay. Did Dave send you in? No, okay, sorry. He said he was going to send some of his students in here. Any questions about what we've done? So the next one is even more bash. Are we all ready for that? We're not just going to be running over the file that's input. That's still going to happen. We're going to run a job for each one of those files, but now we're going to be also iterating over a parameter that is used for the network architecture for our neural network. Okay. So all of those are canceling. Let's list our log files. So again, remember, like we set up, we had our job name as the prefix, job ID, and then we have our little array number there as well. Yeah, you have a question?
Yeah, what did you do to cancel all of them?
Oh, they're just canceling by themselves.
Oh, okay.
They're complete. Yeah. If you ever do need to cancel a job, you would just, so if you wanted to cancel all of the jobs in the array, you would cancel the job ID. If you wanted to just cancel one of the jobs in the array, you would do the whole thing with the underscore. So it's cancel and then the ID. All right.
What is the difference between cancel and kill?
Okay, so cancel kills the processes that or the jobs that have been submitted. Kill kills processes that are running like live in front of you. So it's just a completely different thing. Like kill is a termination command for Linux commands. So I don't use it very much on Hyak. I find that I don't need to as much, but I do have to cancel jobs sometimes if I'm like, oh no, it's doing something bad. The log file is all messed up. So have you had to kill something?
I didn't realize there was a difference.
Oh yeah, okay, so it is different, but the cancel is just gonna cancel things on Slurm. It's not gonna cancel any other processes that are running on Hyak. Yeah,
Okay.
Yeah. And then just so you know, kill will kill it gracefully, the process. Kill -9 will it's dead, okay? But maybe not gracefully, so just be careful. Okay. All right, moving forward. So the next script that we're gonna talk about is Locator NN dropouts.slurm. Nano. Oh wait, before I do that, you guys can go ahead and be in that, but I just want to list the output directory so you can see what's there. So now, this was from our first two jobs, the interactive job and then the unsupervised batch job. And then all of these ones that start with array are the ones that we just launched and had completed. So for each one of these predlocs, you have that same file that we talked about that has the longitude, latitude, and the sample ID. All right. Now I'm going to do the nano thing. Okay, like I said, this is where bash becomes really, really useful for you, because we're going to be making some more variables to talk about. All right. So first of all, I just want to go ahead and set up the accounts that we've been using this whole time, so I don't forget. All right, all of the rest is the same, except we have a bigger array. All right, so this is the situation where you have still your 5 input files for sample data, and you still want to apply all of the same job to all of them. But now you have this other parameter, and it's the one that we're using today is called dropouts. So in neural networks, they can be learning and kind of training themselves, and it might be that you have a limited sample, but for whatever reason they're overfit. So maybe there is a problem that you think that this is not really going to be broadly applicable to the full black cottonwood system, and you want it to get rid of some proportion of those nodes or those points in the network, and so it's called a dropout parameter. It's a way to regularize your neural network. So that's just a little bit of background. But Locator neural network has a bunch of parameters that you could be iterating over. And I'm using kind of the analogy of a parameter sweep. So let's say, okay, you've got all your input files that you want to test on, but you also don't know what is the best dropout proportion to use. So you want to run the same jobs, but with with 3 different dropout values, and this script will help you to automate that. So if this applies to you, this could be really helpful. I'm going to walk through all the variables. But remember that we had 5 input sample data sets, and we're going to have 3 dropout values. So if we get all combinations of those, then we have 15 total jobs that we're going to launch with this array. Each single input value is going to have one of the 3 dropout parameters for each job. Okay? So that's why it's 0 through 14 is the total size of our array. Same thing with the log. And same thing with our file list. It's the same variable as before. We just are inputting a list of the files that are going to be our sample data going in. This is where the fun begins. So we're going to take our Slurm array task ID, but we're going to divide it by 3 so that it keeps on starting over for each one of our dropout values. I have another table coming up, you guys. But that's going to give us a file index so that we have this attached to our file, and it will help us to build the file variable that we'll pass in as our sample data. And so this looks a little bit different. Remember before we had file list was attached directly to the Slurm array task ID. But instead, we're going to use a task ID that's divided by 3. And that will become clear in a second, hopefully, if I explain it correctly. I'll come back to that one. So here are the other variables. So these are really just bonus variables that I'm including in this demonstration to tell you that there are great ways to make your script as generalizable as possible so that you don't hard code the paths to the input values that you're using. You can use this variable input matrix, and then if I change the input matrix at any time, I can just change this line and not have to change what's going on down in the commands. We only have 1 command line in this script, but you could imagine that if you're continually using this input value over and over again to do a lot of things in your protocol, having to go and change all of those at all of the lines can be really taxing and is prone to human error. So if you just code a variable for that one time, then you just have to change this line in your script, and it's much better. Same thing for the output directory. It's all going to be the same for every job that I'm using, but I'm coding these here. All right. The dropouts variable is actually this vector, and these are the 3 dropout parameter values that I want to use to test with this experiment. So 0.25, 0.5, and 0.75. That's why we're dividing this Slurm array task ID by 3. Is this correct? Yes. All right, and then the way that we get to of these dropout values, the way that we get to the specific dropout value that we want is we have our Slurm array task ID and we use a modulus, which gives you the remainder, to find which of the three should be attached to each job. Finally, just for debugging purposes, like with Python, you can put print statements to see what's happening with your variables. You can use echo. You can say the file index for this array is file index, and then file and the other one. And it's the same command as before. Now you have your matrix with the variable input matrix. You still have your file for sample data. Now you have this new argument, dropout proportion, which you're passing in the dropout variable, output directory, giving it a prefix, putting the dropout value, and the file index there. All right, let me show you the table. So this breaks down all of those variables. So for our array of 15 jobs, Slurm array task ID is 0 through 14. File index is the one that was divided by 3. And remember, for each file in our list, we want to have a dropout, and there are 3 dropout values. So we want to run the job on each file 3 times. So our file index will be 0 for the first 3 Slurm array task IDs, and that will be our input. For the next 3 jobs, so you're dividing these by 3, that will be the input. And finally, for your dropout values, it's cycling through. So for each one of these Slurm array task IDs, it has a different one, but it's using modulus. So dividing by 3, if you have the remainder of whatever the Slurm array task ID is, divided by 3, it's really easy to see it. Anyway, it tells it to repeat and go to the front of the vector again, so that you get each one of your dropout values for each job. And finally, the outputs are showing that you have the output directory. The dropout sweep is the prefix that we gave it. It's showing each one of the dropout values and the file index. So then you know that all 3 of these output result files are going to have the ending of 0 for our pred 0.txt. And same. All right, any questions? Are you familiar with the modulus operator? Okay.
Thank you very much.
Yeah, you're welcome.
Question on the out notation.
Uh-huh.
You've got the %x_%a, and I'm just trying to remember where from within the script is it getting the values for each x, capital A and A.
Yeah, so they're up here at the top. So the log files and the final one, it doesn't have to do with the variables that are down here. The only variable that is changing here is going to be the array. So this %x is the job name. This %A is whatever the job ID is that's going to be assigned to the job when we submit it. And then the little a is 0 through 14. Yep. Okay. Yeah, so all of these columns that are showing on the screen are coded down below using all the variables that we set up. This is the only one that is just using this top material here. So if I go back, the output, we've coded this output directory as /. That's giving our output directory. I just put this as so there is a way in Slurm, they have other environment variables as well. So there's probably like a Slurm job name variable that I could have replaced with this since this is the same. But the %x won't work down here. And then dropout is from the execution of this operation, and then the file index is from above. Okay. Let's do something fun here, just for fun. Let's just comment out the command, and then we'll look at the log files just with the echo. And we'll just look at what all of the files are. So if we sbatch locator and then dropouts, basically what it's going to do is it's just going to echo all those statements and show us what our variables were. Which would be better for demonstration if it went faster. Here we go. Yeah, so they're all canceling very fast. So these were the log files that were output. Another thing to notice is that they've all been executed at a different time, right? So the ls-ltr command is showing me the most recent job that executed. So the very last job that executed was actually 0. These are all running in parallel, so it doesn't really have anything to do with in what order. They'll all like finish up when they're done, right? So that's why they've all kind of appeared at different times. Just slightly different times, right? So we'll look at this one. So this is showing file index for this array job is 0. The test set being used, and it's showing me the file that it's using, and then the dropout. That was the first in the vector of 3 dropouts available. So if I go back up and change this to 1, we're still on the same file index, but the only thing that's changed now is the dropout variable for this job is 0.5 and then 0.75. Now when we go to the third job, or sorry, the fourth job technically, third indexed, then we're changing now to the next file index, which is the next sample file, and it started over at the new dropout, back at the first dropout. And same thing. So using the echo statements, you can start to see, without running and executing your command, you can do the troubleshooting beforehand to make sure that all of your variables are correct. And then we can go back in.
So
Mm-hmm.
I see you're using cat. I don't see where you use echo.
In the script, right here. Yeah. So I was just so these echo commands are actually going to be printing these statements and the value of the variable into the log file, because I commented out the command, so it's just executing the commands that are available, and the only ones that are doing anything in that case are the echo commands. So this is saying like, okay, I've set up all these variables up here, but I want to include these commands so that I can see what their values are before executing this, because who knows, this is a really fast job, so it doesn't matter as much. Like you can debug in real time, but if you had a long running job, maybe you want to get those all first. Yeah, test them all first. So those are all just kind of like printing, echoing to the log file. But now I'm going to turn on the command.
Can you remind me what cat does?
So echo will just print statements. I haven't tried. We'll try it in a second. But cat is usually, it's just the concatenate command. So it just like prints the contents of the file to the screen. Yeah, and you can use that in script, but it gets kind of weird. So because it's a different kind of command, you have to use like parentheses and money sign in Bash to be able to use it in your script. Okay. All right. So I've uncommented this. And now I'm going to execute it. And it's the same thing, except that this time our log files will show everything, all of the output from Locator running, not just the echo statements that we had in there. And then also it will produce our output files. Since the command was commented before, it didn't give us any of the output files that we were waiting for. So now if I go, oops. Oh, there they are. So now they're all running 15 in parallel. So now we see we have our log files with dropout sweep and then the job ID and that array small ID. And if we do our out, yeah, we started to see all of the weights and the params, and all of these are like the pre-files that will eventually, so these are the JSON and the weights, those are the files that are available when the job is running, and then the final output files are the predlocs, JSON, text file, and PDF. So let's do that again. So now we see most of our jobs are completing, are done, and we have all of our results here. So in our output, we told it to write to this output directory. We asked it to have a prefix of dropout sweep with our dropout variable that we had printed in the file extension or the file name. And then just to keep everything separate so that we know that the index file, so the poder m pred 4, all of the ones that have this extension of _4 are from that input data set. So that is, yeah, that's what I wanted to display. So the main idea of all of this is that scripting can be leveraged to automate your tasks, and you can also use the features of Slurm, like the array feature, to really get the most of your time and your access to Hyak supercomputer. And so hopefully you'll be able to adapt these scripts for yourself. They are available to you in the directory that you just downloaded, and they'll always be there. Do you have any questions? Yeah.
So you use text files in your example. Does that also work with CSV files, or like when you're trying to kind of making that trading and that the predicting using text file, does that also work with CSV files?
Yeah, it would. Yeah. So they actually are CSV files, but I just have them as .text, but they're like comma separated. So the genotype matrix is a tab separated, but all of these sample files, they actually are comma separated. I just put the wrong name on them. Oh no, they're tab separated. Never mind. But the outputs are comma separated. The main idea is for Locator, you have to follow the rules that they want for their file types. So there might be some adjustments that you need to make. You always have to follow the input guidelines for the software that you're using. So that's really more of like a Locator question, but did you mean for CSV that is there something else that you're trying to do?
So like if I have like a CSV file that's like a training data, and then I have like some kind of like another CSV file like that's like validation data, but I have a couple of like validation data to run. Just check the like the output of the validation data. I'm wondering if there's something similar that I could do with the approach that you did to take here.
Yeah, so I think I would recommend to follow the guidelines of the code that you're using. So if you just have some other software that is running TensorFlow, then I would consult, like if it's a software package that's using TensorFlow to build the neural networks, I would consult the documentation and the guidelines for the input files of that. Locator specifically, these are the exact type of input files that they take. There are a few other types of input files that they take. But I would say with the software that you're using, you need to follow the guidelines, and you'll see errors if you have something wrong. But there might be some TensorFlow programs that have like a Python script just like this that take arguments and stuff where the input is a CSV. But you might have to convert that if it doesn't take CSVs. Yeah. Yeah.
So from within Python, I could run things in parallel by requesting multiple cores and then using multiprocessor and things like that to distribute jobs that way. Is there a advantage or disadvantage to, for example, instead just using the job array to submit to multiple cores that way? Or is there's some like interplay for efficiency where I request 16 cores, have each job run at 4, but then use an array and create 4 jobs?
It depends what you're trying to do. So on your Python command, there are softwares that they're not just trying to run the same job in parallel, like I've demonstrated here, but they might actually be subdividing the task, and then that would be able to use different threads of the machine. So that's called like multi-threading, and that you might only have one job, but you'd want to make sure that the CPUs per task on the SBatch directive matches the number that you're telling Python are available to it. But I think this demonstration is really most helpful if you have that same thing, but you have a whole bunch of similar jobs to run. Yeah. So there are jobs, like you're saying, that are parallelizable, but not necessarily needing to be distinct jobs. They just need more resources, and they need to be coded to be able to access that. And same thing for this job, I only requested, one core per job, but it could be that all of the separate jobs that I need could utilize like 16 cores or something, so you can do it that way. It's really a distinct skill set, or a distinct type of job.
Do you maybe have a sample for us of how you would recommend running something like a checkpoint partition?
Yes. So if I'll just start with a SLOC jobs, an interactive job. So if I want to start up an interactive job on checkpoint, it's going to look a little bit different. So you don't have to put an account, but I'm part of 2 accounts, so I'm going to do it anyway. So this all looks the same.
How about a longer running job? Like what I'm concerned about is having a longer running job on there and then getting like kicked out.
Right.
So even if I put in checkpoints, I don't want to, constantly leave on job. And
Okay. So checkpoint, right. Okay, so that's good. Basically, you would just change the partition. That's the only difference with submitting it. There's a little bit different for GPUs. But checkpoint has a maximum runtime on the jobs. So for CPU-only jobs or HPC jobs that don't have GPUs, the maximum runtime is 4 hours. So your job will end in 4 hours if you don't end it before that time. And it will end in 4 hours whether it is complete or not. For GPU jobs, it's 8 hours. So it will end in 8 hours. You have a little bit more time. It will end in 8 hours. But there's another reason why your job might end, and it's called preemption. So checkpoint is our community idle resources. So when someone adds hardware, they always have on-demand access to that hardware. So like the AMath, you have priority to all of those partitions. For checkpoint, those are just when like all of the AMath computes go to be in checkpoint when someone's not using them. But if you were to then request a job from AMath with that partition, if there's no other room or no other way for the job scheduler not to kick out someone else's job, then it will run your job just fine and their job will keep going. But once the queue is high enough, it will start to preempt checkpoint jobs that don't have priority to those resources so that that we can guarantee that your job will be able to run. So if your job is preempted, it will automatically start over again. So it will re-queue, but it won't save its progress. And that's the big thing. So just like with the 4-hour wall time or the 8-hour wall time, you kind of want to build in checkpointing, that's why it's called a checkpoint partition, into your usage so that your job has the resources available to save its progress and pick up where it left off. And so with training, fortunately, there are weights that are collected with training a neural network, for example, and you can tell the application to pick up where it left off. And then we also have another tool that we haven't tested very much. I don't think it works very well with containers. There's a lot of disclaimers about it. DMTCP, it's a module that we have. And this is another way. It just allows you to save the progress of your job and then start up again. And really it does it at regular intervals. So that's one thing too. You would want to say to your training algorithm every hour, every 30 minutes, every 15 minutes, whatever it is, to save its progress, to checkpoint that step so that you can use checkpoint. Yeah.
So where do we have to, do I use it in the Slurm script?
Yes. Yep. And same with checkpointing with the weights as well. I don't have any examples on me for how to set that up though. but that is something that would be good for me to have on the website. So noted. Yep. I know the checkpoint, it's really good for if you have just a bunch of like quick jobs and that, it won't be running a super long time. So if it requeues, it's not a big deal. But yeah, we would like to make it as useful as possible for folks. So.
So if we're launching a bunch of jobs, why do we have to put them in the array rather than just use a for loop?
Oh, it's because so the array is allowing you to run all those jobs in parallel, so they don't run serially. Like with a for loop, you would get one task done, you would have to complete a task before the next task could start. So instead, the array allows you to launch all of those at the same time. So we could, with what we did, do a for loop on all those 15 jobs that have the different, we could have 4 on the file, and then run Locator 3 times for each of the dropouts. And then once that loop is done, it would go to the next file and then run 3 times, and the next file and run 3 times. But each one of our jobs today, we're taking like 30 to 40 seconds. So times 15, you're about 15 minutes or so, 15 to 20 minutes to get all of that done. Whereas if you're launching them all, it's just 40 seconds, boom, everything is done. So that's the beauty of array. And there are more parameters. Locator is just an example I have off the top of my head, but there are dropouts, there are weights, there are layers to the network. You could do all combinations of all the parameters that you want and really do a parameter sweep. And if you use the full Populus trichocarpa dataset with 30,000 columns, right, it's going to take a lot more. That's like 6,000 jobs. Maybe you have even more like sample data sets that you want to do. It's just going to be to your benefit not to use a for loop.
If he has like one big data set, would you recommend splitting into smaller data sets to be able to parallelize like that?
It depends, I guess, on if your performance or whatever the metric you're trying to get out is going to suffer from not having all of the data. But yeah, I think that it could be useful to split things up. So and if it doesn't matter to like split up, you could use the like Slurm array task ID variable, that indexing variable, to kind of like build the range in your data set of like maybe the rows. You could say, oh, for this one, do rows, this through that or something like that. So I would have to see it to have better ideas, but I could see it working like that. All right, well, that's all I prepared for today. Thank you so much for coming. I'm going to stay here until 12, and then I have office hours at 2 p.m. on Zoom. So again, just so you know, we have our blog on the same website, and I always update the office hours that are available every month. So if you go here, you can click on this register for the Zoom office hours, and that will give you the link to come to my office hours this afternoon. And then oh yeah, so I'm at hyak.uw.edu. This is our main site. And we have our documentation. That's where the tutorials, the material for this session was here on the underneath the advanced Slurm tutorial. And then if you click on this blog section, this is where I always keep updated the office hours for Hyak. So on Wednesdays, I have 2 p.m. on Zoom, and Thursdays I come back here to eScience, but out in the lounge part, and that's where I hold in-person office hours. If I'm not available, I always have a substitute. And then this last section, the Research Computing Club officers, so some student users, they also hold office hours as well. And then if you can't make it to those times, send me a help ticket, help@uw.edu with Hyak in the subject line, and I'll be able to find a space where we can talk to each other.